Hi there, this is technically the last installment of the video series about discovering compounds pharmacologically similar to ketamine. Let's go on to our remote computer. What we have here is the XP with expanded sampling output file that we ran from the SP compiled file in the last video that we ran. What I first want to do is scroll all the way down, and we'll notice that I've sorted this by docking score. Docking score is a metric of how well the molecule or protein ligand is going to fit inside the binding pocket of the protein from a three-dimensional perspective. It doesn't necessarily mean that the molecule will actually bind to the protein, but we'll say that molecules that have a higher docking score statistically are going to have a higher probability of actually binding to the protein if you were to run an in vitro assay. So anyways, we can display, I'm only going to look at maybe the first 10 ligands. The docking scores aren't that great, actually. Typically in a screen, I'm looking for something more negative than -10, but being that the co-crystallized ligand actually lands a docking score of about -6, I remember running that file. A lot of these ligands we would have to sort through. We'll take a look at the first maybe 10 or so. We have to display the protein in the binding pocket by double-clicking it. Table. Top ranking ligand. This is our top ranking ligand. I want to select about the first 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ligands. File. And we can zoom in. Alright, back. Let's take a look at this and see what the situation is regarding the binding pocket. A lot of these ligands are occupying a similar 3D space. One of the issues that I kind of talked about last video, what I thought was an issue, is that if you look at this binding pocket, you'll see there are some ligands that are occupying within this binding pocket, two separate subsites. As it stands right now, this video series is technically complete. Okay. So we have that first ligand. Just take a look at what it's doing. We have a hydrogen bond to the threonine 646, it looks like. And also over here, a hydrogen bond with threonine 648. Okay, that's the common feature of this top hit ligand. Just look at the second ligand. I mean, structurally, these are all fairly small molecules. Oh, that's occupying that other site. That's occupying that sort of other site within the binding pocket. Okay, this is occupying that. Same as the first site, you can see the two hydrogen bonds with those threonine residues. Same hydrogen bonds as we saw before. Same situation, notice the same hydrogen bonds, the threonine, okay, 646, 646, okay. That's just an analog of the compound that we just looked at. Analog. That's somewhat similar to that first compound that we saw on the screen. But same thing, the hydrogen bonding comes up with these more negative docking score ligands. 648 and 646, both threonine residues. Okay. If you want to see a few more of the ligand structures, you can click the top entry. I'll scroll down to, say, negative 7.5 approximately. That leaves us with 89 ligands. 2D viewer. We can see the structure of all of those 89 ligands. They're all small. We'll call these are pretty small molecules. And there you go. As it stands, this project, the overall outcome is complete, right? We would need to either make these molecules or buy these on a service like Mallport, do some in vitro testing to see if they actually bind to NMDA receptor, and that's as far as I'm going to take this one. Thank you guys for coming along on this video series. I'll probably do more video series similar to this about other types of proteins and molecules that act inside the CNS. Thank you. Bye-bye.